Okay, so this is going to be an example of Nearpod. So I hope to show you some of the ways in which I love to use Nearpod in this lesson. And what I love about it is that it allows me to directly assess whether the kids are really paying attention, whether they're getting it, and they have mixed feelings about it because it really does not allow them to drift off. They're not really able to drift off into doing other things while the lesson is going on. They really have to kind of stay with it, and I hope to kind of show that you can see how that's going to work in this lesson. So the students will go to join.nearpod.com. And then the website will come up, and then they enter the code BSQTF, and then they join. And then you might just sort of have them sign in. I will be grading this, so I would always have them sign in with their either first initial and last name or something like that, something that I can identify who they are. Because this is not connected to any other learning system, any management system. Okay, so then they're going to join. Okay, all right, so today's lesson is on electronegativity. And just by a show of hands, who here has ever played basketball? So I'm going to ask the kids, and I'll see the hands go up, and I'll say to them, for the most part, do they know who this is? Do they recognize the players and things like that? Who's your favorite basketball team? Who's your favorite player? And it's a great way to get the kids kind of like into the lesson. And I'll say to them, if you've ever played basketball, even once, okay, you know everything there is to know about electronegativity. You know this already. You don't even have to come to the lesson. You already know. So you're going to see that by the end of the lesson. Okay, so like I said, we're going to talk about electronegativity. If you've ever played basketball, you already know. But before we get to the actual lesson of today, let's review what we did last time. So what Nearpod has is a little bit of a review game, a quick sort of a kind of a quiz game. They pick a character, and then they sort of get started. They answer the questions, and whoever answers the questions most quickly and most accurately wins the game. So that allows them to compete with each other. So you'll see 5 quick questions will pop up, and then we'll just click the answers. Most of the known elements are, these are the choices, and then their little characters will race up the hill. Okay, metals are not brittle. So they're racing up the hill. Ionic bonds, we talked about this in prior lessons. This actually goes back 2 lessons, maybe even 3 lessons. So I'm really checking in on them, keeping them up with their knowledge. Ionic bonds are formed by metal and non-metal atoms. So the ability to transmit heat, electricity, is a property known as conductivity. Okay, and so you'd see like 25 or so characters running up the hill. And whoever's doing the best is going to be in the lead. And metallic bonds are different than ionic bonds because they could be held loosely among metals. So my character rushes to the end to win. Okay, so it's a fun way to just get the kids back into reviewing what they did before. All right, so moving on. All right, so like I said, my basketball players, if you've ever played basketball, what do you think this means? So you're dribbling the ball and you stop dribbling and you're holding the ball. What's the first thing that happens? Tell me. So they'll say, well, this and this happens, but the first thing that happens is somebody reaches in and tries to grab the ball right out of your hands. So if you're going to hold the ball tightly, you're going to be able to keep possession. If you're not holding the ball tightly, you're going to lose possession, right? And so atoms are the same way. They can hold their electrons tightly, in which case things will happen, or they can hold their electrons loosely, in which case different things will happen, right? So what I want you to think about is just like a basketball player holds the ball tightly and loosely, atoms do the same thing with their outer shell electrons. All right. So think about this for a second. All right. Just think. Just curious to know, from a team point of view, is a team stronger when one person holds the ball? Okay. Now don't shout out. Think and talk to your neighbor. Talk to somebody nearby. Okay, your neighbor or the person next to you, and is the team stronger when one person is holding the ball tightly or when the ball is really shared between teammates? Okay. Which is the better team? The team that has what they call like the old ball hogs, right? A bunch of ball hogs, one or two kids that are great dribblers, but they refuse to pass, or a team that really passes the ball. So don't shout out, just talk. And the reason I've been doing these think pair shares is to make the talking, because sometimes you have one or two kids that are always shouting out the answers. This allows every kid to kind of pitch in and to contribute and to share. So here's where I'm going to call on some of the kids that may not like to kind of talk a lot, but I can kind of, given that they're sort of warmed up already, I can get them to kind of like chime in. And there's no right or wrong answer, but we're going to just get them to think about that, like, you don't have to always be holding it tightly. Atoms don't have to always be holding their electrons loosely. There's no right or wrong way, but different things will happen in different scenarios. Okay. And that's what electronegativity is. Electronegativity is how tightly or loosely an atom holds its electrons. So that's the formal definition. All right. So here's where I now switch to a demonstration. So what I have up in front of the classroom, I'll have a beaker with some nice blue copper sulfate solution in it, and I have some steel wool, this gray colored steel wool, and I'm going to dip the steel wool into the beaker, and what you see is that it immediately starts to turn this very bright brown, this vivid brown color. The brown is the copper from the copper sulfate. The copper comes out and it gets all embedded into the steel wool. It starts to coat the steel wool with this copper color. And you see that happens very quickly. Maybe you have to swirl it around a little bit. So I get a chance to show them something. So here's an actual chemical reaction. And then what I want them to do is I want to check in to see what they think they saw. What, in their own words, really what happened. Now, if we're sort of in like we are now, like in a learning remote scenario, if they want to talk it out and sort of record an audio, they can. They can also just type in what they think they saw. If I had shown them a video or something, describe what actually happened. So this is their chance to be, to use the scientific method, to be an observer. And so I always like to get their observations for this, because, some of the kids, for them, like, they don't like the quantitative stuff, but they love to describe things. So this gives them a chance to do that. So I give them a minute or two to work on that. And then here, okay, so here, I guess I had been doing this lesson earlier, so let me just erase what I had drawn before. Now what I'm going to do is we're going to start to turn, and whenever we do chemistry, so it's a common theme in my class, we're always using the periodic table. We are never going to do chemistry without having the periodic table open right alongside. Okay, so we use this tab here. This would be open all the time in our class, the dynamic periodic table, the online periodic table, and I'm going to ask them to circle the transition metals. So here I would ask them to go ahead and circle the transition metals, and that's essentially what I'm looking for. And what I see on my end as the teacher is I'll see 25 different slides pop up on my screen, and I can see, did somebody circle this? And I can say, hey, Ryan, what do you think about, are the transition metals with these noble gases? Is that something you'd think? Or think of oxygen. Does that sound like a metal? I can really get them to kind of like rethink what they're doing. Or if somebody circles, all of them, kids, they are doing all kinds of funny things with with what they're, if they know the answer or they don't. But it allows me to kind of like dig in a little bit and see who's really thinking their way through this. So I love that. I love to kind of just get their feedback and kind of interact with them along the way. So um, moving on to the next slide. And now we're going to have the periodic table open. Uh, there's a link they can click on. But what happens here is that they're going to look not at the, they can click on this link here, not at the typical kind of periodic table, but here using this uh, periodic table that shows the electronegativity values. So what they're looking at, they can see, I can ask them, well, what do you guys see here? What do you see? Well, you see different shades of brown, right? So there's a very light brown here all the way to the very dark brown here. And you see these numbers, right? And I'll ask them, what's this number up here on the left, right? So what is that? Oh, that's not the electronegativity, right? That's the atomic number, right? So what is it down here? This is your electronegativity down here on the bottom. So for cobalt, you'd see electronegativity of 1.88 and so forth and so on. So I try to sort of orient them to the actual electronegativity values of each element. Okay, and then just give them, just to check in, I could say, all right, guys, circle for me the element that has an electronegative 2.02. So they have to look around and check out their Chromebook and see where they are. So they say, oh, here it is. I found it. Bismuth has a 2.02 electronegativity value. And then they have to find 1.33, which turns out to be zirconium. And I'm going to look to see who's circling what. Are they able to really sort of read and zoom in and know, oh, here's the electronegativity value? Okay, so that allows me very quickly online in real time to see who's able to grasp, what it is we're actually looking at. Okay, and then very quick little quiz to kind of check in. It says that the element, and the kids they tend to be really into these quizzes because they really want to get the answers right. So and so but if it's too long, it's overwhelming. So I usually found like 3 questions right in the middle of a lesson just to kind of pep them up. Are they following along? And I'll ask them. So, open up your tab. Which element has the highest electronegativity? So they're looking around, and probably by this time they may have noticed. I might clue them in to say, check out the color, the shade of the color. That's going to be a hint. Say, oh, fluorine has got the highest electronegativity. Okay, and this are next. Now, hold on. Did I skip a question? Oh, the lowest in electronegativity is francium. Did I skip one? The highest electronegativity is fluorine. Right, okay. And then francium is the lowest. And then, okay, so based on its electronegativity, fluorine probably holds its electrons very loosely, very tightly. Okay, so this is what they may not know. They may not know, well, I know it has the highest electronegativity, but does that mean it holds electrons tight or loose? So, we're going to talk about it, okay? We're going to talk, and I'm going to ask them, what do you guys think? What do you think about question 3? And we'll sort of get some feedback there. And, I'm going to let them know. High electronegativity means you're holding your electrons very tightly, okay? So that's it. So we know what electronegativity is, and we know that there are specific values for each element. Each element has an electronegativity, which is on the periodic table. So you can look it up. All right. So moving along. Where are we here? Okay, it gives you your score. That's great. All right. So good job, everybody. All right. So you know what electronegativity is. You can look it up. Now, let's apply it, though. Let's apply what you know. So let's do some chemistry, okay? So do you remember the demonstration I did at the beginning of class? Okay. So remember I dipped the steel wool into the copper sulfate and then it came out brown. So here, what I want you guys to do is, sorry about this, these are my previous answers. So the kid screen would be blank. I'd say put a blue X where you see the copper sulfate. So I say something like this. I see the copper sulfate. And then I say put a black X where you see the steel wool. So they do that. And I say, okay, now, and show me a brown X where you see the copper. So I know it seems overly simplistic, but I want them to I want to know that they really know what it is they're looking at. So what's this brown stuff? It's copper. What's this? It's iron, it's steel. What's this? This is the copper sulfate solution. So it allows me to check in to see, do they get it? Okay, copper versus iron. Now we're going to get really specific. We're going to really compare um, uh, these two atoms. We're going to get right down to these two atoms. And what I'm going to ask them to do here, the instructions are to look at this image. All right. So this is an image from the periodic table. You see iron here with an electronegativity of 1.8, copper with an electronegativity of 1.9. And what I tried to do is make a kind of an analogy to how tightly they're holding onto their electrons. So here's a little boy holding onto his soccer ball, and he's holding onto it pretty tight. That's a 1.9 electronegativity. The copper atom is holding onto its electrons pretty tightly. Iron is holding onto it more loosely. So this guy's got his volleyball, and he's holding onto it a little more loosely, and that's reflected here in iron having a lower electronegativity. Okay, so I can read the caption here. Copper and iron have different electronegativities. One element holds its electrons more tightly than the other. And you can think of this like a child at a park holding onto a ball, right? So examine the image, pay attention to the electronegativity value and how high and how tightly each child is holding onto their ball. Now, imagine that an older kid comes along, so like a bigger kid. He shows up and he says, "Hey, I would like to take one of the balls." Um, you know how kids are. So one kid sees another kid with a ball. He says, "Hey, I'd like to play with your ball," right? So, and this guy's going to hold on to his ball real tight, and this guy's like got his ball hanging out there, like, okay, well, whose ball and whose electron is going to be taken? Who's going to have? Okay, so imagine an older child comes along and wants to grab and take away the smaller child's ball. Which ball do you think is going to be taken away? Is the volleyball going to be taken away or the soccer ball going to be taken away? Based on what you see here, who's the more likely to lose the ball, right? I would argue the volleyball, right? The child's not holding onto his ball very tightly, so it's likely to be ripped away from him, on the playground. Okay, no problem. Okay, so let me just erase my answers from before. All right, now imagine, okay, we're going to just continue with this analogy that um, the older child is like the sulfate ion, right? So we had copper sulfate solution. There's a sulfate ion there. The sulfate has a choice. It can grab an electron from copper and react with copper. And that's how it starts out. That's copper sulfate. Or it can grab an electron from iron. It has a choice. Whose electron is it going to grab? Is it going to grab the copper ion? Remember, copper is holding onto its electrons very tightly. It has a higher electronegativity. Or is it going to grab the um, electron from iron? So who's holding on to their electrons more loosely? It's the iron atom. So the sulfate ion is more likely to grab electrons from iron because iron has a lower electronegativity. Okay, so again, I'm just erasing my prior answer. So imagine have you ever seen a child who holds their ball very tightly? Sometimes you go to the park, you see a kid, he's got his ball, he doesn't really want to play, he's holding on to it real tight. Okay, this is the child that's sort of left alone, right? They just rather not play. They don't want to lose their ball. So, and so think about that in terms of electronegativity, right? So copper is holding on to its electrons very tightly. At the end of the reaction, all right, who's left alone? So you see that brown color. That brown color is what? What is the brown color? What element is that? I'll sort of take a survey. The brown element is copper, right? So copper is left alone. It's sitting by itself in its nice, happy copper color state, and it's by itself, right? So because it has a higher electronegativity, it doesn't want to share its electrons. Copper is the atom that's going to be left alone. Sulfate is the one that's going to, iron is the one that's going to be reacting with sulfate because iron's electrons are more easy to grab. Okay, so that's basically the basic idea. So I just, what I'm hoping is that the kids really kind of have grasped the relationship between reactivity and the concept of electronegativity. And now here's their chance to do the experiment themselves. So here's where I make sure everybody gets their safety goggles on. Everybody's going to get a chance to go back to their benches, to put their computers down, and to go to their benches, get up from their seats, go to their benches, and take a look at and get a beaker, and I'll have the materials out there: beaker, some copper sulfate, the steel wool or a nail. They can use an iron nail and get a chance to just do this on their own. And they love this. They love swirling the steel wool in the solution, and you see what color it changes. Okay, so here, once they're situated with all their safety gear, I'm ready to go. All right, so guys, go ahead and do this experiment yourselves. So they can, it doesn't really matter how much copper sulfate you put in, half a spoonful. It's not a quantitative thing because it's not meant to be a full-fledged, extensive experiment. It's just meant to be a quick activity where they get to dip something in something and see something fun happen. So it's meant to be quick and simple. All right. And I want to ask them, and what I'm doing now as this is happening, I'm going around the classroom, checking for safety, checking to see that everybody knows what they're looking at. So when I see the brown stuff, I'll say, what is that? And hopefully I'm looking for the answer copper. Why is copper coming out of solution? And I'm looking for the answer because it has a higher electronegativity. It doesn't want to react. So I'm looking to see if everybody can kind of like give me that feedback as to really what's going on. So after I've had a chance to go around, the kids, this video is just an example of, I just cut it off the web of some other kids who did the experiment, put it on YouTube. If you wanted to watch that, you could see for yourself what the experiment looks like. So here now, as we get to the end, what I'm going to do is wrap it up. So what I'm going to ask the kids, okay, wrap up. Everybody back to your seats. Wash your hands, get back to your seats. And what we're going to do is we're going to ask them to just review what they saw. The nail turned what? What color did the nail turn from? It turned from, and hopefully to hear, the kids shout out gray, and it turned to brown. Okay, why? Why did the nail turn brown? And I'm looking for this answer of, that it had to do with its electronegativity. Okay, now these are two final sort of summary wrap-up activities that I usually put at the end of my lessons in Nearpod. And this is really just to get a chance to use the vocabulary, to use the terms that we've been talking about, and to really kind of put the whole story together, the whole narrative. As negatively charged electrons swirl around the positively charged nucleus. And here's how I prompt the kids. I'll leave the blank, or I might call on someone who maybe doesn't shout out much, and get the kids to kind of really participate. However, the electrostatic force that is exerted on the valence electrons can differ from one atom to another. The strength of this force determines how tightly an atom can hold onto its outer shell valence electrons. This is known as electronegativity. In today's lesson, we use the periodic table to determine electronegativities of different elements. The periodic table shows that copper has a higher electronegativity than iron, and that it should hold its electrons more loosely than copper. And we discovered that the sulfate ion can form bonds with both copper and iron. But since iron holds its electrons more loosely, the iron will react preferentially with the sulfate ion. Okay? In the reaction copper sulfate with iron, the brown substance is copper. Okay, so I'm just looking for them to use the vocabulary. And then the last sort of wrap-up activity is a matching game. They just match the items. This is a quick one. It's fun. It's just a fun activity. That's what I love about Nearpod. It has a lot of these little activities built in to the lesson to keep them going, to keep them interacting, to keep them participating, and not just sort of like nodding their heads. So you see the iron nail, you're matching iron, you see high electronegativity means holds electrons tightly. Loosely held means low electronegativity. Negative charge goes with electrons, positive charge with the nucleus. And this gives them a chance to do that. Okay. Now, this is the final sort of like coach in the center of the huddle, me in the center of the classroom walking around. This is sort of my favorite part of the lesson is, guys, it matters, right? How much your team passes the ball matters. How much your team holds and dribbles the ball matters. It matters a lot, right? NBA championships are won and lost because of, very, very tiny differences in how much passing and how much dribbling is taking place. Okay. So it matters. All right. And why in chemistry does it matter? Why in chemistry does it matter? Because different elements hold their electrons more tightly or loosely. And the more tightly you hold your electrons, the less reactive you are. Okay, so think of an element that's not reactive. Gold, for example. Let's take a look here down here at gold, right? Gold has a very high electronegativity, 2.54, right? Gold doesn't react with anyone. Gold is gold. We love gold. Why? Because it doesn't react with anyone, because it has a high electronegativity. Okay, so in chemistry, it matters a lot about what kind of substances, what they're going to do, and how they're going to behave. A lot of it has to do with electronegativity. All right, so that's basically where I'd end the lesson. In terms of the timing, this may be a little too long. I may have packed a little too much in here, but I can cut it short, or I can pick it up, or the kids can take this as a finish on their own later kind of activity, sort of in an asynchronous way, finish it up. But for some kids, they may be farther along. They may have already, I see this a lot. They'll race ahead, and this is an optional activity for them to earn a few extra points, extra credit. Here is a chance where they get a chance to really look at a video on the reaction mechanism, and then what they're doing then is to look more closely. But I want them to think about rust, right? Because a lot of people see this brown stuff and they think, oh, it's rust. Well, is it rust? What is it? How is it different than rust? And so as they look at the video and they start to see, I'm not going to show you the video, but this is something they would do on their own. As they look at the video, what the video does, I'll just sort of like jump through it here, but it's going to get into the actual reaction mechanism in very, much too much detail for college prep chemistry. But for the kids that really like to see what happens, they can really see what's going on. But what I want them to see this FeSO4 and ask themselves, is that rust? Right? Is that the same thing that you get when you leave a nail out in wet weather? So this is where I hope some of the kids that are really into chemistry will come up and really get a chance to talk about this, maybe offline, maybe during lunch or something, to kind of just like let them go a little further. So anyway, that's the lesson on electronegativity, and I'll just sort of end it there.